Uno, dos, tres, cuatro.
Hi Pre-Calc 12s, welcome to the first lesson on our unit on radical and rational functions. Today we're going to look at radicals, and it's a bit of a review, but what I would also add is that the entire chapter is a bit of a review from Pre-Calc 11. If you had done the equivalent questions from Michelson and Pre-Calc 11, I would say you could probably come into this unit where you would probably be able to know more than 50% of the content already, if not even more so. So anyways, take a look. I don't know if you've ever seen a real life square root before, but in terms of a real life square root, here we go. Take a look at that. Okay, so radicals. Let's go through some terminology and let's see what we can recall from the past in terms of radicals. So a couple review of some terms. The value inside of here, this n right there, that's called our index. Now typically it's we work a lot with square roots, so if there's nothing labeled there, then we know there's a secretly denoted a 2, and that would be a square root. What's underneath the radical is your radicand, so in this case our a would be our radicand. For the second example right here, we said that if there's nothing there, it's denoted as a 2, so our index is a 2, and that's saying it's the square root of 7, and our radicand would be a 7. Okay, so now if they say find, what would happen if x squared equals 1? Some of us jump to the gun and say, well, x equals 1 is your answer. And just, I want you to get into the mindset of remembering that actually if you square root both sides, then x is going to equal plus or minus 1. It creates a positive and a negative situation. Because if I put in negative 1 and I square it, I still get positive 1, just like if I put a positive 1 and I square it, I get a 1. So it could be plus or minus 1. You need to say both of those to be able to have it. A second way that you could actually also look at this as a solution is if you had something that said x squared equals 1, you could always subtract 1 onto the left side, and what you've done is if you factor that, you've produced a difference of squares. So it could say x plus 1, x minus 1, whoops, and then your solutions would be x equals negative 1 and x equals positive 1. So that's a possibility as well. X cubed equals negative 27. So if we take the cubic root, then the cubic root and the cubed would reduce with each other, and we'd be left with something in which x would be equal to negative 3. So one thing that we should review is to see how to be able to put in other roots into our calculator and to see what would happen if you had something like that. So this next question here is saying, what's the fifth root? What's the fifth root of negative 13? So I'm just going to pull up our calculator right here, and I want you to take a look at what would happen if you press math and then you go down and either select 5 or go down to 5 and press enter. And that's how you can draw upon some sort of random root. So right here, we're going to say we want the fifth root. So my index is 5. I'm going to press to the right, and then I get my 13 right here. And if we do something like that, then we should be able to get an answer of 1.67. Okay, so let's go back here and let's see what we have. So we'll say this was negative 1.67. Okay, and then for the fourth root of negative 13, we could put that in our graphing calculator, but we know that if you have an even index, like a 4, you could never have a negative radicand. Okay, you couldn't have the same number 4 times, an even number of times, and having it produce a negative number. So because of that, anytime you have a situation like this, just like if you had the square root of negative 13, we know that's not allowed. So you would say that there's no solution there. There's no answer for that. Okay, so let's take a look at a couple more examples here. If they want to find something out with the domain and the range, The domain and range for just a basic square root function would say, well, x has to be, it's going to be defined for values greater than or equal to 0, but it also means it's going to produce an output that's going to be greater than or equal to 0. Whatever you put in for x is going to produce a number that's going to be at minimum 0 or more. So y is greater than 0 as well. And let's actually skip straight to c. Let's do c next. And we want to do c next because it's also an even radicand. And because of that, it's actually going to have the exact same characteristics. It would only be defined if x is greater than or equal to 0. Likewise, it would only produce outputs that are greater than or equal to 0. So when you have an even index, hopefully you can see the pattern of what's happening there. If you have an odd index, like we have here with a 3 or a 5 for part B and part D, then we could put in any number that we want for x, because you can have a negative or a positive and it would still work out. Think of the example we had earlier where we had the cubic root of negative 27. When you took the cubic root of negative 27, it was negative 3. It can still be found. And the y value could also be anything as well. And that's going to be the same for our fifth root. We can call that a quintic root as well. And so right here we come up with the generalization. The domain is a set of all real values of x at all times except any value that causes a negative number radicand with an even index. Okay, so we're looking at what are sort of good situations and what are bad situations, and we're saying here's the restrictions that we have for A and C and the restrictions that we have for B and D. Okay, so let's see what we could do for this next part here. So this is a review in terms of graphing, and we have A, B, H, and K, and those are representing parameters, and we want to remember what that can do if we have some sort of transformation happening. And I know we've been doing a lot of transformations, so let's take a look at what would happen with something like the value of A. So A, the first thing is if there's a negative there, then we know it could potentially have a reflection over the x-axis. And we also know that the a value acts on our entire function, so it's telling us what sort of vertical expansion or compression is occurring. Let's go to the b value next. The b value would tell us what's happening if you have any sort of reflection over the y-axis. And then it would also tell us if we have some sort of horizontal expansion or compression. And that's because it's directly connected to the x. The h value is going to be our translation, and it's going to be our translation left and right. And then our k value is going to be our translation up and down. Hopefully that seems like review from some of our previous units. Okay, so to see what we can recall about in terms of our graphing of transformations, let's see if we can graph these next four. And these next four examples, they're all going to have something that's going to be a little bit different. So you can see here's our C and D. In order to do this, a couple reminders. So number one is you always want to be in what we call ready position. And ready position means that we've isolated for y. And then the next thing that you want to do is you also want to make sure that you apply what we call our rect order: reflections, expansions, compressions, translations. And then the final thing that I would say is because we're graphing square root functions for each of these, you want to remember what a basic square root function is. So whenever you start off with one of these questions, I would begin by plotting 0, 0. And then I would have just your basic square root function points drawn in there. And it's based off of y equals root x that you're going to apply these transformations. So looking at this first one right here, we know that the first thing we need to do is we would need to subtract 6 onto the other side. And then we want to label what's happening with each of these transformations. So I would say here, this 2 is in front of our function. It's to the left of the square root, and so it's affecting some sort of vertical expansion or compression. And we know that if we have a 2 there, then that would be a vertical expansion by a factor of 2. We're also going 4 units to the left and 6 units down. So based off of that, what you would do then is you would look at your y equals root x function that we have right here, and we're going to see if we can vertically expand it by a factor of 2, meaning we're going to multiply all of the y values by 2. And then after that, I'm just going to do a dotted line to represent this guy. And then after that, you want to shift everything 4 left and 6 down. So if we were right here, we could say 4 left, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so then based off of that, this would be your final function. So from there, you can answer what the domain and what the range is, and it looks like our domain would be everything greater than or equal to -4, and our range is everything greater than or equal to -6. So here we can say domain is x is greater than or equal to -4, and range is everything greater than or equal to -6. For part B, to put it in ready form, we need to multiply both sides by 2, and that would eliminate the y. And if we times this by 2, we would get something that would say y equals -2 root x minus 1 plus 2. Oh, I made a mistake there. This 2 on the right side gets distributed, so it gets distributed to that root as well as to this plus 2 part, so we could say that would be a plus 4. And if we want to label what the different things are happening here, we know that there's a negative in front, so we have a reflection over the x-axis. We have a vertical expansion by a factor of 2. And we know that we're going 1 to the right and 4 up. Okay, so from there, let's graph our basic function. And let's reflect it over the x-axis. Vertically expand it by a factor of 2. And then you want to move it 1 right and 4 up. Okay, so based off of that, for the domain and range, our domain would be x is everything greater than or equal to 1, and our range is everything less than or equal to 4. If you're feeling confident about this, why don't you pause the video now and see if you could come up with part C and part D, making sure that you put it in ready form and then you apply your rect to y equals root x. So for part C, 4 minus x is backwards, and to account for that, we want to factor out a -1. When you factor out the -1, it still stays inside the root, so it would be root negative bracket x minus 4. And so that would be the exact same thing, but it lets us apply our transformations a little bit easier. So now we know that we have a reflection happening over the y-axis because the negative is connected to the x value, and then we're going to be moving 4 to the right and 1 up. So from there, if we reflect this over the y-axis now, it's going to look like this. And then from there, we want to go 4 right and 1 up. Okay, and that would be our final. So if we want to answer for that, what's our domain and what's our range? Our domain would be everything less than or equal to 4, and our range would be everything greater than or equal to 1. For part D, we need to factor out that 2 that's inside. If we have 2x minus 4, remember that's not saying that we're going 4 to the right. We haven't factored out the 2. It actually means we're only moving 2 to the right. So we need to put it in ready position. And then based off of this, we should be able to say, let's graph our original function. And from here, we should reflect it over the x-axis. And then after we've reflected over the x-axis, let's just label what we're doing here. So we want to reflect over the x-axis. We have a horizontal compression by a factor of 1/2. And then we're going to go 2 right and 1 down. Okay, so we've already reflected it over the x-axis. Let's horizontally compress it by a 1/2. Whoops. It'll look like that. And then we want to go 2 right and 1 down. Okay, it might not be the clearest, but that is our final graph. Okay, so that started when x is at a value of 2, so x is everything greater than or equal to 2, and y is everything less than or equal to -1. Okay, so some additional questions that could be asked from this would be something like this. Can you create an equation for something like this? Could you say what would be this radical function? And there's actually more than one way we can answer it. So the way I would begin with is I would look at what your starting point is. Where's it been transformed to? It looks like for part A, we've gone 7 to the right and we've gone 3 up. So based off of that, my guess is we would have something where we've gone 7 to the right and 3 up. And if you think about what a typical square root function looks like, normally you go over 1, up 1, and then over 4, up 2. Well, here if we go over 1, we went up 2. And if we went over 4, 1, 2, 3, 4, we went up 1, 2, 3, 4. We went up 4 units. So our up value is twice as much as what our original function was. If we go over 1, up 1, and now we go over 1, up 2, we have a vertical expansion by a factor of 2. And we can represent that by putting a 2 in front of here right there. So that would be one way of answering it. So I'm going to keep it like that, and I'm actually going to go on to the second part. Let's say let's call this part B, and let's see what we would have with something like that. And then maybe I could say that there's more than one possible answer. So for part B, we've gone 3 to the right. There's no up or down movement. We're on the x-axis, so you don't have to put any vertical translations there. And it also looks like it's been reflected. It's been reflected over the y-axis. And so if it's been reflected over the y-axis, then we probably want to make an adjustment for that. And you could say negative x minus 3 like that. If you wrote 3 minus x with no brackets, that would also be correct. And again, if we go over 1, normally you would go up 1, but now we're going up 2. So we're doubling our up value again. It looks like it's been vertically expanded by a factor of 2. So we'll put our 2 in front of our function there to represent that vertical expansion. So I'll pick one of these and I'll just play around with it a little bit more. So if I look at A, I'm going to give you a second solution that could also work. So it's not that we're going to ask for this, but if you had written something like this, if you wrote y equals root 4 bracket x minus 7 plus 3, this would be saying, hey, instead of having a vertical expansion by a factor of 2, I also actually had a horizontal compression by a factor of 1/4. Okay, so how does something like that happen? So if you think about this, normally if you go, let's see. If you think about what your original function would look like, if I went over 4 and I went up 2, think about what would happen here if you said, well, what if we go over 4, 1, 2, 3, 4, and if I go up 2, well, normally it would look something like that, but now I've actually only gone over 1 unit horizontally instead of 4 units horizontally. So I'm horizontally compressing it by a factor of 1/4, and that would be represented in the way that we wrote it right here with that 4 inside the brackets. And to give confirmation that that's also right, you could actually separate that. What if you took out the square root of 4 and you said, well, if I take out the square root of 4, I would now have 2 on the outside. I'd turn it into a mixed radical, and I'd be left with root x minus 7 on the inside. So we know that these two are definitely equivalent to each other. So in this case, we're actually saying that means that a vertical expansion using the square root function by a factor of 2 is equal to a horizontal compression by a factor of 1/4. And that's going to be true for square root functions. So you could do the same thing for part B, and you could have also said y equals negative 4 x minus 3 like that. Okay, our next part here is saying, can you graph the cubic root of x? And we haven't done this, I don't think we've done this before, but if you know what x cubed looks like, this is just graphing its inverse. We're going to turn it on its side. And so if you pick some values here, you could say if I put in 0, I get 0. If I put in 1, I get 1. If I put in 8, I get 2. So I picked perfect cubes to be able to help us out with this. This would be -1 and -2. And then quickly we could plot what that would look like. So you would have 1, 1 and 8, 2. And you would get something that would look like this. So from there, this part B here is now saying, could you graph the transformation after it's gone, after it's reflected over the x-axis, and it's going 1 right and 2 down. And so if you take a look at the graph we have right here, and we reflect that over the x-axis, we could do that, and then we want to move 1 right and 2 down. And that would be our final solution. Okay, hopefully that part seems reasonable. Just adding to our different tools of different types of transformations that we can shift around. So that's moving around a cubic function. Sorry, a cubic root function, I should say. Okay, another thing that we have is you might fall into something in which they're asking you to take the square root of a random function. And so if you look at example 7, you'll see these aren't really random functions. If you take a look at that, that looks like it's a linear function, and that looks like a quadratic function, but we're not going to be worried about finding out their specific equation. We just want to say, can you take the square root of any sort of function there? And so a couple things to review. The first thing is the term invariant point. So an invariant point is something that remains unchanged after a transformation. And so if you think about taking the square root of something, what would be a number that you could square root so that when you square root it, it equals the same value? So for example, the square root of 1 remains 1. The square root of 0 remains 0. And so those are two examples of invariant points. So there's a couple steps here, but basically let's go through this and let's see what would happen if you wanted to square root a function. So if you look at 7, first example right here, at 1, when you take the square root of that, so if you had the point xy and you square root your output, your y value, at 1, nothing will change because the square root of 1 is 1. Just like right here, the point 20, nothing will change because when you square root the 0, it stays at 0. But for all of these values below the x-axis over here, if you square rooted them, you'd be creating something that wouldn't work. If you take, for instance, the point, if you had the point there that was 5, -2, and you tried to square root that y value, then you'd be square rooting a negative number, and all of that would disappear. So nothing's going to be below the x-axis at any point. If you take a look at the steps here, it says try and find some perfect squares that could create something that's nice and clean. So for instance, if you have a y value of 4 and you take the square root of 4, the square root of 4 is just 2, and you would now create something that would look like that. Okay, so that would be our way of being able to square root functions. Why don't you pause that right now and see if you could square root this the second one right here. Okay, so we know that we have invariant points when y is at 1 and when y is at 0. And we know that anytime you have negative values, if you take the square roots of those, you wouldn't produce anything that would be defined. And then you want to pick some perfect squares. So if you take a y value of 4 and you square root that, it would drop down to 2. And you would get something that would, let's see, something that would look like this. Okay. All right, let's look at our final example for the day. So now they're saying let's take a function that we can graph. We could graph y equals 1/2 x squared minus 2. We know that's a parabola. It would be a parabola that has a vertex of 0, 2. And if we plotted 0, 2 right here, and it has a vertical compression by 1/2. So the amount we go over, we square it to go up, and then we half it. So if I go over 1, I would go up a half. And if I went over 2, I would normally go up 4, but now I go up 2. And if I went over 3, 1, 2, 3, I would normally go up 9. Now I'm going to go up 4.5. 1, 2, 3, 4.5. And let's do one more. If we go over 4, I would normally go up 16, but now I'm going to go up half of that, so I'll go up 8. And I would create a parabola that would look like this. So then based off of that, we want to be able to create a square root of that function. So we've completed part A. That's what part A looks like. And so for part B, can we now square root that function? So never try to do part B right away without having done part A. So you'll see some questions in your homework that ask something like that. You always have to graph the original function first, and then we're going to see what its square root would look like. And so if we want to graph its square root, again, let's highlight where y is at 1 and where y is at 0. And then anything below we know is gone. And then we can find out where we have a y value of 4. And we could take the square root of that and drop it down to 2 to create something that would look like this. Okay, so if you need some clarification from any of those examples, make sure to ask me in class. Otherwise, that's your introduction to radicals, and we have some homework being assigned right here. So good luck with that, and that's all for today. Thanks.